limit and cluster point. We first start from definition. Okay, limit point or cluster point. Here these two are different. Okay, first we start about limit point. Let X be a matrix space. Let X be a matrix space. Let X be a matrix space. Let E subset of X, E subset of X, and a point X belongs to capital X is a limit point, of E, if and only if for every r greater than 0, for every r greater than 0, we have BXR intersection E not equal to 5. Okay, then this one is called limit point. That means X minus R, X plus R intersection E not equal to 5. This one is the definition of limit point. Okay, we take a ball around X of R radius, and then E, if E this, then E intersection this not equal to 5. Then we call about this X the limit point of E. Okay, now start this one by some questions. Let E be a subset of a matrix space. Let E be a subset of a matrix space. Let E be a subset of a matrix space. Okay, then we have to show that any X belongs to E is a limit point of E. Any X belongs to E is a limit point of E. Okay, E be a subset of a matrix space. We have to show that any X belongs to E is a limit point of E. That means if we take any subset of a matrix space, then we find X around X one ball of epsilon radius. That means Bx epsilon equal to X minus epsilon, X plus epsilon for epsilon greater than 0. And this ball intersection E not equal to 5. If this ball intersection E not equal to 5, then this implies that X be a limit point of E. X be a limit point of E. Okay, now we start next questions. Where is these things? We just see limit point definition and start this portion, limit and cluster point. Okay, so next thing we deal about now, one question: if a subset of B and X belongs to X is a limit point of A, is a limit point of A, is a limit point of A, then then it is also a limit point of B. Then it is also a limit point of B. Then how we do it? We know about that x be a limit point of A. This implies that we construct a ball BXR intersection A not equal to 5 for r greater than 0. This implies that x minus r, x plus r intersection A not equal to 5. Obviously here here we write a subset of B. Okay, here we write a subset of B. A subset of B. If a subset of B, then x minus r, x plus r intersection B not equal to 5. This implies that BXR intersection B not equal to 5. This implies that x be a limit point of B. Okay. Now we see another example. Find the limit points of of 0 1 open, 0 1 closed, and 0 closed 1 open. Okay, and obviously 0 1 closed in R. How these limit points are? That means if you take any point between 0 1, x between 0 1, then BXR intersection E or intersection this 0 1 not equal to 5. Even we take 0, then B0R intersection 0 1 not equal to 5. Okay, same thing B0R intersection another all sets given here, all intervals given here, that means 0 1 not equal to 5. This implies that 1R, sorry, this one 1R. Okay, then we implies that 0 1 close interval 0 1 be the limit points set of this interval. Close interval 0 1 is the required answer. Okay, for all these limit points be these, this interval limit point this interval limit point this interval limit point this in R. Next we're going to further questions. How we deal limit points. Okay, next find the set of all limit points of Q. Limit points of Q in R. Limit points of Q in R. We take any point x belongs to U, then BXR intersection Q is not equal to 5. Okay, then x be a limit point of Q, and in R limit points of Q in R equal to, that means x belongs to R, any point, then BXR intersection here Q not equal to 5. Then any point of x belongs to R, intersection Q not equal to 5. This implies that x be a limit point of Q. Then the limit point set be R. Because x be arbitrary, since x arbitrary. Okay. Then next we erase these things also. Now we're going to every open set containing x has a non-empty intersection with E. That means this one is the concluding part. Okay. Concluding part is x be a limit point of E if and only if every open set containing x has non-empty intersection with E, has non-empty intersection with E. If we take x be a limit point, of E, this implies that bxr intersection E not equal to 5. This implies that x minus r, x plus r intersection E not equal to 5. This implies that we take any open set U, intersection E not equal to 5, because U equal to, we construct this one. Okay. That means x where U will be open. Next, every open set containing x. That means next thing, x containing U intersection E not equal to 5. Okay, this one is given. Then we have to prove that x be a limit point. Then we construct, and also given U be open. U be open given. So we construct U subset of x minus r, x plus r. Then this U intersection E not equal to 5 implies that x minus r, x plus r intersection E not equal to 5. This implies bxr intersection E not equal to 5. This implies that x be a limit point of E. Understand? Now we're going to further discussion about here. Here we going to in topological space. If a subset of x of a topological space X, a point x belongs to X is said to be a limit point of E if every non-empty open set that contains X contains a point of E. Okay. Now we're going to another theorem, another important theorem about this limit point. A subset E of a matrix space A subset E of a matrix space xt is closed. xt is closed if and only if E contains all its limit points. All its limit points. Then first we start about the assume that E be closed. Assume that E be closed. Let X be a limit point of E. Let X be a limit point of E. Let X be a limit point of E. If X belongs to E, then nothing to prove. Okay, that means X be a limit point and X also belongs to E. If X does not belongs to E, then the set U equal to X difference E is open. And X belongs to U. Therefore, there exists an R. There exists an R greater than 0 such that the open wall BXR intersection E equal to phi. This contradicts the assumption that X is a limit point of E. Therefore, we conclude the statement X does not belong to E be false. In other words, any limit point of E lies in E. That means this means that any limit point of E lies in E. Okay, X does not belongs to E, then we proceed further. Then you take U X difference E is open also, and if E be closed, then E complement or X difference E is open. Then X belongs to U, therefore there exists an open wall such that this intersection E obviously phi. This contradicts X be a limit point of E, so X does not belongs to E is false. In other words, any limit point of E lies in E. Now conversely, how we handle if E contains all limit points. If E contains all limit points, then we want to prove that E is closed. Okay, then we have to prove E be closed. Consider u equal to x difference e. We need to prove that u is open. We need to prove that u be open. If u is not open, if u is not open, it follows that there exists x belongs to, it follows that there exists x belongs to u such that for every r greater than 0, such that for every r greater than 0, such that for every r greater than 0, the open wall is not contained in u. The open wall bx are not contained in u. Okay, that is, there exists r greater than 0. The open wall, that is for every r greater than 0, there exists a point in complement of u. There exists a point in complement of u, hence x is such that hence x is such that for every hence x is such that for every hence x is such that for every r greater than 0, for every r greater than 0, Vx are intersection E not equal to 5. Okay. So we E contains all limit points. To prove E closed, we construct x difference E, then we see that U open, then E be closed. If U is not open, then there exists an open wall which does not contain in U. That is for every epsilon a point in complement of U. A point is complement of U means a point in E intersection bxr is not equal to 5. That is, x is a limit point of E and is not in E. This implies that x is a limit point of E and not in E. This one is contradiction because all limit points, E contains all limit points. Okay, so U be open, hence U be open, then E be closed. So contradictory, we prove this one. First we see if E be closed, then E complement be open or U be open. If U is not open, then we find x bx are intersection E not equal to 5, that means X limit point and not in E. So U be open and E be closed. Okay. Next we proceed another corollary about this theorem. We just write this one now. Corollary is that a subset E of a matrix space is closed if and only if a subset E of a matrix space HD of a matrix space XD is closed if and only if the following condition hold. The following conditions hold. Okay, what is this condition? If xn is a sequence in E, converging to X belongs to X, then X belongs to E. Okay, now we start with an example, one familiar example. Here given that C01, the set of all real valued continuous functions on 01, a subset of B01 under norm infinity. Okay, then F belongs to B01 is a limit point of C, then F belongs to C also, and hence C is closed in 01. And another, this one is corollary, that means a sequence in E converging to X. Okay, then X belongs to E. Now we see that C equal to C01. Okay, C equal to C01 be the set of all real valued continuous functions, be the set of all real valued continuous functions, on 01. Okay, subset of B01 under the norm infinity, then F belongs to B01 is a limit point of C, then F belongs to C, Okay, then what we find? We find C is closed in B01. That means C equal to C01 closed in B01. This one another important example. C01, set of all real valued continuous functions, is closed in B01. Okay, so today we stop here.